Ranak everybody, we continue talking about difference in statement and how it influence on a result of simulation. So today we talk about comparison linear and nonlinear behavior in reason of material. We do some calculation with linear material and we do some calculation with nonlinear material, and let's comparison them. So first of all, we need to see that our deformation is 0.5657 and our stress, with 10,000 of megapascals, it's around 243 megapascals. So let's add some nonlinear materials, and we can find an engineering data source on general nonlinear materials. We can find couple of steels. It's stainless steel and structural steel, and you can see that both of them has similar, not equal but similar characteristic about Young's model. It's about 2,000 of gigapascals, something like that. And we have two different yield stress. For structural steel, it's around 250 megapascals, and for stainless steel, it's about 210. So, if we take a look to this result and we see 243 megapascal, we can think that for the first hour task with force around 10,000 of newtons, we will not obtain any plastic result, any plastic stress and strain. But if we take a look to nonlinear task, and we also can see that we have the similar forces. So for the first second it's about 10,000 of newtons. So for the first step of time, for first second, we see that our deformation are bigger, not 56, 57, but 62.62, and equivalent stress not bigger, not higher, but less. It's 233 megapascal. And if we take a look into plastic strain, we'll see that we have some plastic strain in one elements in corner of this place. Why do we have plastic stress and plastic strain in those places if we have stresses less than 250 on this solution, and we have less than 250 on this solution, and this is linear. So for general thinking, we can't obtain here any plastic stresses, any plastic strain, any plastic behavior. But if you will take a look here, display option, you will see that we have averaged result for all these elements, and you see that it's almost smoothed. Yep, it's not very smooth in some places, but it's much smoother than its original stress distribution. If we will take a look here, we can see some different version of option of visualization. We don't talk about all of this today. We will talk about this option later. But let's change averaged to unaveraged version. So we change to unaveraged. We retrieve this result, evaluate this result, and we see that the maximum are not 243 megapascal, but 400. And we see that maximum stress are not here, and even not here, but here. Hide this body, let's take a look. And we see the place with the maximum stresses. And we see that in those nodes we have maximum stress 400 megapascals and very small stress about 43 megapascals. Here 230, 240, 155, 130, 140, something like that. So when we create averaged result for this point, for this node, we'll obtain less than 400 of megapascals. And with all other objects, with all other nodes, we obtain the same behavior. And if we take a look here, we will see that we have 280 megapascals of stress, 312, and so on. So that's why we obtain a result with plastic behavior, because on this element we have strain that more stress and strain that more than yield limit. Okay, we obtain that and we understand that. Now let's do another comparison. This is linear task, and if we will increase our force from 10,000 to 30,000, sorry, my fault. So if we change from 10,000 to 30,000, we will obtain a very simple result. All stresses will increase and the picture of distribution will be the same. We see difference only in maximum of stresses if we will use automatic scale. This is adequate for stress and for deformation because we have fully linear task. Material are linear, contacts are linear, it's bonded. Let's check this. We select the last result and now we see 56 and 243. So we have 1.5 and almost 700.5 in the end. Let's obtain those results and see. We see 730 megapascals, and as you see, results are not changed here. Yep, if we change here something like that, red is stresses which are more than stress limit, yield limit, we'll obtain some changes in picture of distribution. But with original scale, we see the same picture. And for deformation, results are the same. On a third result, we have the same picture and we have 1 and 7. Okay, so we understand a result which we obtain with linear statement, with full linear statement. Let's take a look into our nonlinear statement. We will select the last result, retrieve them, and we have not 730, we have only 380, so twice less. And we see that picture of distribution are very different from 10,000 of newtons of loss. For total deformation, if we obtain evaluate the last result, we will see not 0.62, sorry, I don't retrieve, but 20.5 millimeters. So it's in 40 times more. 40 times, not in 3. And again, we have 40 times more result in deformation, and we have twice less in stress comparison with linear statement. Why it's so? If we return to our materials and we see nonlinear behavior, we will see that tangent modulus, it's a stiffness of material after yield point, is 100 times less than original stiffness of linear material of linear of elastic model and so on. So that's why we have such a big difference in deformation, because all plastic places, places with plastic behavior, with yielding, work not with 2E11, but with 2E9. So work with stiffness 100 times less. That's why we obtain results in 40 times more. But stress behavior, so this is how we must work, and this how we work. And that's why we have not so big difference in stress. It's a stress. And this is deformation. So this is small difference in stress, and this is very big difference in deformation, in translation, and so on. And you need to understand that this line is almost horizontal because angle 100 times less. It's almost horizontal. So those difference will be bigger. This one will be less, even less, and this one will be even bigger. Okay, we understand that. We can see plastic result, and we can see plastic result for the last point, and we see that that's a lot of plastic, and maximum plastic it's about 9%, and blue it's not absence of plastic, it's around 1% of plastic. So if we change this one, for example, to E -5, sorry, it's almost zero. It's not zero, but it's almost zero. We will see that all our construction work with some plastic behavior. Not with 100 times less stiffness, but with some percent of plastic behavior. Okay, we understand that. But there are one but there are one additional thing that we need to explain. If we return here to our 1 second to 1000 of newtons of load and take a look to this result, sorry, and here we must return, we'll see that we have 243 megapascals of stress in those places. Okay, and we already talked that for linear behavior with very small mesh, this mesh it's almost default, it's 15 millimeters, and this mesh is 2 millimeters, so it's very good mesh. And we have almost the same result in deformation, and we have the same stress distribution for sorry, I'll try this result, and we have almost the same stress distribution for 10,000 newtons, for 20,000, for 30,000 of newtons. We have the same type of stress distribution between 15 millimeters mesh and 2 millimeters mesh, but in some places, in some small elements, we have much higher stress in reason of hot spots, and in reason that in linear statement stress here in this point must be an infinite. So changing size of elements are not very change behavior of model for linear task. We have better result, we have more accurate result, but it's not change in big way our stress distribution, deformation distribution, and so on, if we have adequate mesh. But if we came to nonlinear task with 2 millimeters, on the 1 second where we have force about 10,000 of newtons, we have almost the same result, because we almost doesn't have nonlinear behavior here. We have almost the same stress distribution picture, but we see that our stress much higher. Not 233 as it was, but 360. And we have some place with plastic, which we see here. But if we take a look here on the result, we see that we have almost 0.2% of plastic strain here on this place. And if we return to our 15 nonlinear, if we return to our first second, we see that maximum here is 2 E minus 5. So it's 100 times less. Let's apply this value to our this model. 2.3 3 E minus 5. And we see that we have much more place with a plastic deformation. Sorry, it's airstrike. We have much more places with yield strain and yield stress. Unfortunately, it's close, so I will finish faster than I want. Okay, we have much more plastic strain here, and that's the reason that we have different behavior. And if we take a look to the last result, horizontal, we will see that we have 12% of strains, and we see very different picture from this mesh. We almost doesn't have plastic strain here. We have some plastic strain here, and we have only plastic strain here. If we return here, we see that on base bottom we have a lot of plastic deformation. We have plastic deformation which look like this one. We have a lot of plastic deformations here, and we have very different picture of plastic distribution here. And we see equivalent stress that also have different picture, that have another result. Here we have 380. Here we have 360, and with almost the same maximum. It's for the first, sorry. Retry this result. So we have almost 570 megapascals, and take a look to this one, and take a look to this one. And if we create something like this, 250, and do some changes here, we will see much more different behavior. Much more different behavior. And we have a result of stresses with nonlinear solution twice, almost, okay, 1.5 times bigger with the same load as on this mesh. And we have bigger deformation. Just a moment. We have much bigger deformation. It's almost 31. And here we have 20.5. Why? Why we obtain such a big difference with a mesh which will not give any difference in behavior with linear static? Because it's non-linear task. And when we create averaging for big mesh, and when we create averaging for small meshes, we will obtain very different result. And with very big stresses here in this corner, this element are almost linear, in the reason that we have these points very not very close to this one, and average result are less than yield point. If we create mesh with more adequate size, these elements became to yielding, and it will not work. So it will not work with the force. So force became to other elements that present here. And the reason that we have much more accurate stress distribution, we can obtain a result that all these elements, all elements which we have here, will work in yield stress, in reason that we came with different ways. So please be careful, and if you need to work with nonlinear result, you need to have adequate mesh for this calculation. It's a truth for contacts, and it's a truth for material nonlinearities. Have fun, and if you want to obtain all this project, which I will end all these lectures, please become a patron. I will upload files here, and hope you have a peace at your home. Bye.